Hello viewers, welcome again. This is my first episode on the topic magnetic effect of electric current, a topic in Form 2 that many students think is difficult. I believe that by the end of these lessons, you'll be able to grasp all the concepts with ease and explain them with pleasure. Feel most welcome. Okay, let us start with a little history here. We want to dedicate this topic to Hans Christian Ørsted, a Danish physicist who lived in the year 1777 to 1855. He discovered that electric currents creates magnetic fields. I want to put it in layman's language that anytime current flows through a conductor, it produces magnetic field. Anytime current flows through a conductor, it makes this conductor behave like a magnet. That's what we mean by using magnetic effect. In this topic, we are going to look at magnetic fields due to current, Christian Hans Ørsted experiment, magnetic field patterns on a straight conductor and on the solenoid, simple electromagnets, factors affecting strengths of an electromagnet, motor effects, factors affecting force on a current carrying conductor, applications such as electric bell, simple electric motor, and speakers. Since this topic is wide, we are only going to deal with the first 3 points in our lesson today. That is magnetic field due to a current, Christian Hans Ørsted experiment, and magnetic patterns on a straight conductor. You know this? Did you know this? That when current flows in a wire, it produces magnetic fields around it? If you do, then you are a genius. This major discovery was done first by Denmark scientist Hans Christian Ørsted in the year 1820. Procedures followed by Hans Ørsted, and I believe that you can also follow this procedure in the lab. Connect a straight conductor to the battery. Place a compass needle under the wire and parallel to the wire, and then switch on the current. Repeat the experiment with a compass needle above the wire. State and explain the observations seen or made. Observations. It is noted that if you put a compass needle below the wire and there is no current flowing in the wire, there is no deflection in the compass needle. However, if the compass needle is put below the wire and current allowed to flow, it's noted that it deflects in one particular direction. If now you put the compass needle above the wire, it is deflected in the opposite direction. The same can be achieved if you reverse the direction of current. Now, what makes this compass needle to deflect? I'm going to answer that question. Compass needle is just a small magnet. So the reason why it is deflecting is because there is magnetic fields that are produced around that wire carrying current. So these magnetic fields interfere with the magnetism of the compass needle, therefore making it to deflect. Are you following? Alright, by now I believe that you know that a compass needle placed under or over the wire which is carrying current, will experience some deflection. But can you be able to predict the direction in which the north of the compass needle will be deflected? This can be explained by Ampere's swimming rule. So Ampere's swimming rule is used to show the direction in which the compass needle is deflected. So if one imagine swimming along the conductor in the direction of electric current and facing the compass needle, then the north pole of the needle will be deflected towards the swimmer's left hand. So just imagine that you're swimming along the wire facing the compass needle and line the word facing the compass needle. Then your left hand will be deflected to where the north of the compass needle will be deflected towards. I hope you. Are you? Okay, if this experiment was to be done in the laboratory, if you are to put a compass needle over a wire in a complete circuit as shown in the diagram A, you will note that the north of the compass needle will be deflected downwards. Why? Let us use Ampere's swimming rule. Current is flowing from left to right. The compass needle is over the wire. Once the compass needle is over the wire, then you have to swim on your back so that you face it. So you will note that your left hand will be deflected towards the lower side of the wire. In case 2, that is in B, the compass needle is placed under the wire. Current is still flowing from left to right. So if you are to imagine swimming, you'll swim using your stomach facing the compass needle. Then you'll note that your left hand will be above the wire. So the compass needle will be deflected towards the upper side. I hope you're following. I hope you're enjoying. Thank you for being here so far. Tell me what it feel like to have no fear at all and do it here in real life. What have you so far learned? When current flows through a conductor, it produces magnetic effect. I think this is the major point in this topic. When current flows through a conductor, it produces magnetic effect. The magnetic field produced by current on the conductor interferes with the fields on the compass, causing it to deflect. If the compass is below the wire, one has to imagine swimming while lying on the stomach. Just imagine swimming in a swimming pool and looking at a compass needle that is at the bottom of the pool. If the compass needle is above the wire, then one has to imagine swimming on his back. This is equated to swimming on your back while watching an eagle flying above the swimming pool. If the direction of current is reversed, the deflection of the compass needle. It is always good to start from the knowns to unknown. We already know that a magnet has got magnetic fields around it. What is a magnetic field? It is the region around the magnet where magnetic influence can be felt. It is the region around the magnet where magnetic force can be felt. So, what are the characteristics of magnetic field lines? Some of them is that the magnetic field lines never cross each other. They are closest where the field is strong, and they repel each other sideways. They always come from north and go to south. Now that you know that a magnet produces magnetic field, Let us see whether the same will be seen in a conductor carrying current. You know that when current passes through a conductor, it also produces magnetic fields. But what is the nature of these magnetic fields? Are they also coming from north to south? Are they crossing each other? Are they parallel to each other? That's what I'm going to look at in this lesson today. So when current flows in a conductor, it produces magnetic fields. For a straight conductor, the magnetic fields produced concentric circles around the conductor. Concentric circles around the conductor. To determine the direction in which these fields are going, then we can use right-hand grip rule. We already know that they are concentric, but is it clockwise or anti-clockwise? So you can use the right-hand grip rule to determine that. Or you can also use corkscrew rule to determine the direction of magnetic field. State two methods that you can use to determine the direction of magnetic field. Answers: 1. Right-hand grip rule. 2. Corkscrew rule. What is the nature of magnetic field produced in a straight conductor that is carrying current? The magnetic fields are concentric. The magnetic fields are perpendicular to the direction of current. Those are two characteristics. Thank you so much. Alright, to predict the direction of magnetic field, then we do use Fleming's right-hand grip rule. If a current carrying conductor is held in the right hand with the thumb pointing along the wire in the direction of current, then the other fingers will point in the direction of magnetic field. This is self-explanatory. This is so easy. Just take your pen, hold it using your right hand with the thumb pointing towards the sharp point. I'm just imagining that the sharp point is where the current is flowing to. Then these other four fingers will show you the direction in which magnetic fields will face. So like shown in figure 2, if current was flowing upwards, then imagine you holding that conductor with the thumb pointing upwards while holding that conductor. Then the four fingers will show anti-clockwise direction. That is the direction of magnetic field. Thank you for following closely.
I know you're a superstar, a supernova shining, you can see from super far. And they ain't ready, know you're about to hit the throttle on them. Won't see it coming, you gon' come through like a super.
Alright, we can also use right-hand screw rule to predict the direction in which magnetic fields will flow. It states that if a right-handed screw is turned so that it moves forward in the same direction as the convection current, its direction of rotation will give the direction of magnetic field. I always insist that we should not cram word by word. We should just understand physics, then state it in our own words. So if you imagine closing a screw, which direction will it turn? Will it turn clockwise or anti-clockwise? It just depends on which direction you're closing it towards. So imagine that you're closing a screw using your right hand and you're closing it such that it moves forward in the direction of current. Then the direction in which its head will rotate will be the direction in which magnetic field will be facing. You see how this is easy? In diagrams, an X with a circle around it represent current into the paper, while a dot with a circle around it represent current out of the paper. This way. So if you see an X and then a circle around it as shown in the diagram, then current is flowing away like an arrow flowing away into the paper. But if you see a dot, that means that current is coming towards you. That means it's coming out of the paper towards you. So current into the paper, a cross. Current out of the paper, a dot. We can also use iron filings to locate magnetic fields. How? All you need to do is complete a circuit using a wire passing through a hard cardboard. Sprinkle some iron filings on the cardboard and tap it using your finger so that to make the iron filing settle. So because of the influence of magnetic fields that are on the conductor, you'll find that the iron filing will settle down in concentric circle around that conductor. We can also locate the magnetic fields around a conductor in the laboratory by use of a magnetic compass. This one will be able to tell us the direction of those magnetic fields. Remember, the magnetic fields, due to current passing through the conductor, will interfere with the magnetic field of the compass, making it to deflect in some way. So all you need to do is pass current through a wire, and that wire should pass through a hard cardboard. And then place compass needle close to the wire and put a dot at the end of its north pole. Move the compass needle so that its south starts with the point where the dot was. Make another dot at the end of the north pole. Repeat this until you come back to the starting point. Join all the points. You realize that they form concentric circles. Alright, now to the end of the topic today. This topic deals with the study of magnetic effect due to a current carrying conductor. This knowledge was discovered by Christian Ørsted Hans in the year 1820. Ampere's swimming rule can be used to predict direction of deflection of compass needle. Can you be able to state Ampere's swimming rule? Concentric magnetic fields form around a straight conductor. The direction of magnetic fields is either shown by the right-hand grip rule or corkscrew rule. If you see a dot, current is coming from the paper, and if you see an X, current is going into the paper. Our major objective in this topic was to know that when current flows through a conductor, it produces magnetic field. To get that knowledge. 2 is that we should be able to explain Hans Christian's experiment. I hope you can be able to do that. 3, our major objective also was to know the nature of magnetic fields produced on a straight conductor. Thank you very much for following through up to this end. However, I have one request. Please subscribe and also share the link with other friends of yours. Together we can become great. Thank you so much. Have a nice day.